Swayamprabha. Digital India. Educated India.
So far we have discussed about some examples of steady flows in the paradigm of low Reynolds number flow. Now we will discuss something more about steady flows later on, and we will discuss about a theory which somewhat generalizes the elementary low Reynolds number hydrodynamics that we have discussed, and that theory is known as lubrication theory. So, we will discuss about that in details later on, but prior to that let us move into some cases of unsteady flows. So, let me talk about a little bit of motivation as we discuss about the unsteady flows. So, when we discuss about unsteady flows, remember that whatever we are discussing here is in the broad, with the broad motivation of studying some examples related to microfluidics. So, we are proceeding towards that direction in many ways. Now, we will start with an example of an unsteady flow with a classical problem which is not a problem of microfluidics, that is Stokes' first problem. So, the Stokes' first problem is something like this. You have a solid plate and there is a fluid over the top of the solid boundary. This fluid is initially stationary. Now, you suddenly pull the plate with a particular velocity, say u equal to u0. Then because of the movement of this plate, there will be a disturbance in momentum in the fluid which will be propagated by virtue of the fluid property viscosity. So, we want to see that how does this momentum disturbance get propagated as a function of position and time, that is as a function of the y coordinate and the time coordinate. Now, what is the relevance of this problem in microfluidics? See, this is not a microfluidic system, in fact this is not a confined system. Now, in microfluidics there are several effects which come into the picture. One possible effect is the effect of confinement, that is if you make a plate coming on the top of this plate with a small gap between the two plates, then it becomes a confinement. So, the question is that how does the confinement affect the flow? To understand that, we will first solve this problem when we will consider that there is no confinement. See, if we want to understand what is the effect of confinement, first we have to study that what is the scenario when there is no confinement, and then in the next problem that we will be solving we will put a plate at the top of this one. So, this becomes a confinement and we will see what is the difference between the results in the two cases, and that will give us an indication of what could be a possible effect of confinement in unsteady flows. That is one of the classical motivations. I will talk about some more motivation later on. So, as we proceed, so when we get a little bit bored with the mathematical exercise, we will talk about some practical motivation to compensate for that. So, let us start this working out this problem by writing the governing equations. So, let us assume that the velocity u is a function of y and t. It is not a function of z, because the plate is considered to be of infinite width. It is not considered to be a function of x. That is not fully developed flow to be in a literal sense, because fully developed flow we generally talk about in the context of internal flows, that is flow through channels, pipes and all this, but the notion is similar, that there is a translational invariance. That means if you want to look into the velocity field at this location, the same velocity field will be repeated if you go to a different axial location. If you translate and move on to a different axial location, that is called as translational invariance. So, with that u is a function of t and y, or y and t, whatever. So, this is equal to, so the left hand side of the Navier-Stokes equation will have this unsteady term, remaining terms will not be there, because u del u del x plus v del u del y, if del u del x is equal to 0, and as a consequence from the continuity equation v is equal to 0, that we have already discussed. So, that means the remaining terms, if u is not a function of x, the remaining terms are not there, but unsteady term is there. That is the basic difference between the previous problems and this problem, that there the unsteady terms were not there, now the unsteady term is there. And because of the length scales involved, the dominant viscous term is the viscous term which is mu del 2u del y2. The x length scale is being much greater than the y length scale, this term is dominating as compared to the gradients along x. There is no pressure gradient, because it is like an infinite flow medium where it is subjected to like uniform like atmospheric pressure from all sides. So, it is a open problem. Now, of course, I mean you can artificially impose a pressure gradient on this, but just like a flow over a flat plate, you have the flow is acting, flow is being subjected to a 0 pressure gradient, that is also very similar to this. Now, as we can clearly see that the problem is dictated by the kinematic viscosity. So, mu by rho, we can write this as nu, and the problem is dictated by the kinematic viscosity. So, here what will be the time scale? The time scale will be, we have discussed about 3 possible time scales: the advection time scale, the diffusion based time scale and the forcing based time scale. So, here what will be the time scale? It will be the diffusion based time scale, because you can clearly see that these two are competing with each other. Now, there is a time scale associated with the problem, but there is no natural length scale, right. There is no natural length scale involved. So, why is there no natural length scale involved? Because there is, it is not in a confinement. If it had it been in a confinement, the height of the confinement would have been the natural length scale, but it is an unconfined medium. This is like in, this is extended up to infinity. So, there is no natural length scale, but it is important to figure out that what could be a possible natural length scale based on the time scale. So, what is that length scale? Length scale means the distance up to which the effect of this movement of this plate will be felt, right. So, question is that on which factor is that distance related? One of the critical factors on which it is related is time, right. So, if you allow more and more time, more and more fluid in the outer layer will feel the effect of the plate, right. Theoretically, if you allow infinite time, all the fluid will feel the effect of the plate, but in a very short time only a small extent or a short depth from the plate will feel the effect of the solid boundary. Okay. So, time is an important parameter. Is there any other important parameter? Yes, kinematic viscosity, we have discussed about that, that more is the kinematic viscosity, more will be the effect or the penetration depth of the effect of the movement of this plate. So, the length scale up to which the disturbance due to the motion of this plate will be felt should be increasing with time and should be increasing with kinematic viscosity, but exactly how? To understand that, we will make an order of magnitude analysis of this equation, very simple analysis. So, what is the order of magnitude of this term? U reference is u0 by T reference, this is of the order of nu u0 by y reference square. So, y reference scales with square root of nu T reference. Okay. That means, although there is no natural length scale in this problem, but the length scale is eventually decided by the kinematic viscosity and the time scale. Okay. So, from here we can qualitatively expect that u by u0 will be a function of y by y ref, and this function is expected to be self similar. This is very much analogous to the boundary layer theory, where velocity profiles, like if you draw an analogy with the boundary layer theory, if you have this as the boundary layer, velocity profiles at various locations are indeed very different, but if you non dimensionalize or normalize the velocity profile, u by u infinity as a function of y by delta, this being delta, this being the new delta at the new location. So, u by u infinity will be a single valued function of y by delta. Here the delta is this one, that is the penetration depth, just like the boundary layer. Okay. So, u by u infinity is like u0 here is a function of y by delta. See, this delta, it is a function of t, right. This we could get from a physical intuition. So, we can write that u by u0 is a function of y into a function of t, right. This gt roughly scales with 1 by delta. Okay. So, we can, because it is a single valued function of this, we can replace this with a variable eta, which we call as a similarity variable. Okay. And seek for a solution, and when you express the solution in terms of this similarity variable, again just like method of separation of variables, the similarity transformation, the objective is to convert the partial differential equation into ordinary differential equation, because if you are able to express this as a function of eta as a single variable, then it will be a u by u0 will be a function of a single variable only. Question is it always true? I mean, is it always possible to cast this type of PD into in the form of an ODE like this? It depends on the physical situation on hand. In this physical situation it is possible, So, I mean there are situations when that may not be possible, but here the physics is giving us or driving us towards this kind of variable separation. Now, we will proceed with the solution of this problem. So, u by u0 is a function of eta, where eta is equal to y into gt. So, what is del u del t? u0 df d eta into del eta del t, right, using the chain rule. So, del eta del t is y into g dash, right, where g dash means dg dt. Then del u del y del u del y, why we require del u del y, because we need to evaluate this term. So, del u del y u0 df d eta into del eta del y. So, u0 df d eta into g. So, what is the second derivative? Second derivative is u0. So, you basically make d d eta of this into del eta del y. So, another g will come. So, it will be u0 d2f d eta 2 into g square. Okay. So, let us then write this equation del u del t, that is u0 df d eta to y g dash is equal to nu del 2u del y to nu u0 d2f d eta 2 into g square. And what is y? Y is eta by g, right. This y is nothing but eta by g. u0 gets cancelled from both sides. So, g dash by nu g cube is equal to d2f d eta 2 by eta df d eta. Right. So, we have clubbed all functions of t in on one side and all functions of eta on one side. So, this is function of t only, this is function of eta only. So, these two are the same only if each is a constant. So, let us say that the constant is C. So, we can write dg dt g dash is dg dt, then 1 by nu g cube is equal to C. So, g to the power minus 3 dg is equal to nu C dt. So, g to the power minus 2 is equal to by minus 2 is equal to nu C t plus C 1. Now, we have to remember that what is G. So, G is what? G is 1 by G is the penetration depth at a given time, right. So, at t tends to 0, what is G? At t tends to 0, the penetration depth is what? The penetration depth is what? 0. So, G is 1 by the penetration depth, that will tend to infinity. So, at t tends to 0, G tends to infinity, that means C 1 will be 0. So, you have G is equal to 1 by minus 2 nu C t square root. All right. So, you can see, so this is the beauty of scaling analysis. Say a rigorous mathematical analysis has given rise to this form of G, but you could tentatively get this form without going into this mathematical analysis, simply by scaling the two terms that are appearing in the governing differential equation. So, you will clearly get that G scales with 1 by square root of nu t. Remember that G is 1 by y reference. Y reference is scales with square root of nu into t reference. That is what is sort of supported or justified by this more detailed mathematical treatment. Now, the question is, what is the value of C that you may take? So, only restriction is that C has to be negative, because this G has to be a real number. So, C must be negative. So, what is the typical choice of C? So, that depends on convenience. So, you may choose, for example, C is equal to minus half or 2, minus 2, like that, so that you know the square root business goes off. So, as an example, let C is equal to minus 2. So, then remember, this is not a must, this is just an one example. So, whatever C you will take, it does not disturb this equality. So, you recall that in school level ratio proportion problems, A by B equal to C by D equal to K, whatever K you take, that does not disturb the equality of A by B and C by T, that is what is important. So, this equality is never disturbed because of the presence of this C. So, for different C, the solution of G will be affected and the solution of F will be equally affected. So, I mean different C's will eventually give rise to the same solution. So, you will have G is equal to minus 2 as an example. So, C is equal to minus 2 as an example. So, G will be 1 by 2 square root of nu t. This is about G. Now let us concentrate on F. Okay. So, you can see that we have now been successful in converting the PDE into an ODE. We will write the boundary conditions immediately, but before that we will just integrate these ones. So, the boundary conditions maybe we can write first and then integrate. So, what are the boundary conditions of this? At eta equal to 0, what is F? F, what is the definition of F? Definition of F is U by U0, right? U by U0 is F. So, at eta is equal to 0, what is U? U is U0, no slip boundary condition, right? You have to be careful. Here the plate itself is moving. So, no slip boundary condition does not mean that the fluid is stationary. It means the fluid is stationary relative to the solid boundary, right. So, if the solid boundary is moving with a velocity u0, the fluid will also move with the same velocity u0. That is what is the no slip boundary condition. So, if u is equal to u0, then what is u by u0? 1. So, at